The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Okay, I think we're going to go ahead and get started. Good afternoon, everyone. Thank you for being in this session. My name is Kamal Kayat. I'm having the pleasure of moderating this session. Field measurements of formwork pressure exerted by self-consolidating concrete. This session has been sponsored by 3 different committees of ACI: 237 on SCC, 238 workability of concrete, and 347 formwork for concrete. And the speakers that have been selected are all speakers from the 3 different committees. We have speakers to you today from the United States, from Sweden, and from Canada, 5 speakers who will share with us the latest information regarding the measurements of SCC in field applications. Our first presenter is Eric Koehler, Senior Research and Development Engineer from the Verifi LLC in Cambridge, Massachusetts, and he will be talking about Thixotropy of SCC and its effect on formwork pressure. Eric is also the chair of ACI Committee 238 on workability of fresh concrete.
Okay, good afternoon, everyone, and thank you for coming today. So I'm going to talk about Thixotropy. And so why are we here on a Sunday afternoon to talk about Thixotropy? Well, it's because SCC would not be possible without having Thixotropy. And what Thixotropy does for us is it creates a higher viscosity of the concrete when it's at rest than when it's flowing. And that's critical for things like formwork pressure reduction and segregation resistance. So our concrete, as you can see at the bottom, it can be very fluid. It can flow under its own mass, so it has a low yield stress, low plastic viscosity, and it can do everything we expect out of SCC. But by having that Thixotropy there, we're able to reduce the amount of form pressure to make concrete more practical to place, and then we're also able to increase our segregation resistance. So Thixotropy is very critical, and that will be the focus of my presentation. So the first thing I'll talk about is what is it? I'll define it. I'll talk about different options for measuring Thixotropy. I'll also talk about how it relates to form pressure, show some field data, and then have some conclusions. So first of all, what is Thixotropy? So here's the scientific definition, and I actually took this definition. ACI Committee 238 on workability is developing a tech note on Thixotropy. We're very close to getting it to TAC to review, so it hopefully will be published in the next 6 to 12 months. But this is the definition that we use in that document. So Thixotropy is the reversible isothermal time-dependent decrease in viscosity when a fluid is subject to increased shear stress or shear rate. So that's a long definition. Let's talk about the different components of it. So first of all, it's reversible. So that means that when concrete is at rest, the viscosity builds up. When concrete is shear, viscosity decreases. And we can continue that process back and forth, and it's completely reversible. Second part of that is it's isothermal. So when the temperature of concrete changes, the viscosity will also change. But in our case, that's separate from the effects of Thixotropy. So shearing the concrete can create heat in the concrete, and it can affect the viscosity. That's not Thixotropy. And then lastly, it's time dependent. So when we have a concrete that is at rest in the forms, it takes a period of time for that viscosity to build up. It's not instantaneous. And likewise, when we're shearing the concrete, it takes time for that concrete that thixotropic structure in the concrete to break down. So it's also time dependent. So let's start off looking at our rheological model. So concrete is most commonly characterized with the Bingham model. And the Bingham model is relating shear stress to shear rate. So the key terms as part of this model are the dynamic yield stress and the plastic viscosity. So the yield stress is the amount of stress to initiate or maintain flow. The plastic viscosity is the increased stress that we need to increase the shear rate. And most concretes can be characterized with Bingham model. So this is what the model looks like when we don't take into account thixotropy. So now let's also define one more term before we go on. And that's the apparent viscosity. So the apparent viscosity is just the shear stress divided by the shear rate. And so this is what we'll use in the definition of thixotropy. So we have the plastic viscosity that is on the slope of this line, and then we have the apparent viscosity, which is just through the origin. So when we talk about thixotropy, we have a material that's at rest, and we begin to apply shear to that material. When we initially apply shear, we're going to get a higher shear stress. And so if I take this, run a test in a rheometer, what I'm typically going to do is increase my shear rate from 0 to a maximum, and then back down to a minimum. So if I have my up curve where I'm coming from rest and I'm increasing my shear rate, I'm going to have a certain shear stress with that. The longer I shear it and that there's a breakdown of the thixotropy, then we're going to have a lower value on the way down. And so when we typically go into a rheometer and measure the rheology, we're normally measuring this down curve as part of to get the yield stress and the plastic viscosity. Then the area between these two curves is defined as the thixotropy. So the bigger that area, the more thixotropic the concrete. So we have a number of terms here that we can define. We have the thixotropy, which is the area between the two curves. We have the static yield stress, which is up here. This is the minimum shear stress to initiate flow from rest. Then we have the dynamic yield stress, which is the yield stress to maintain flow once we've broken down that thixotropic structure. And then we have plastic viscosity, which is the slope of the line, and we always take that from the down curve. So if you think about thixotropy in time, and we think about, we'll go through this A, B, C, and D. So on the bottom is the shear rate that I'm applying. On the top is the shear stress. So if I start out with a material that's at rest at point A, and the thixotropic structure is building up, so I begin to apply a shear to that material, and so I go up to B, and you can see what happens when I go to B is that I get this high shear stress, and as I continue to shear it, that shear stress drops, and that's because the thixotropic structure is being broken down. And then I can remove that shear from the material, or I can reduce it. So that's what I'll do at C. I'll go from a high shear rate to a low shear rate. So I'm still applying shear. I'm still going to have a shear stress that I can measure, but I am going to see that that's going to increase. The shear stress is going to increase over time because I'm applying a lower shear rate now, and I have a lower. And because I have a lower shear rate, I'm going to have a partial rebuilding of some of that thixotropic structure. So now, before we go on, talk any more about thixotropy, let's talk about some distinctions of what thixotropy is versus what it's not. So first of all, thixotropy is not hydration. So the viscosity over time is going to increase because of hydration, and so that's not covered in thixotropy. Also, during a test or during a placement, you could have segregation of the concrete, and you're going to have a paste-rich region and a aggregate-rich region. That's going to affect the viscosity, but that's not due to thixotropy. And then also, we have what we call a shear thinning fluid, which is where the shear stress and shear rate curve decreases, the slope of that decreases over time. And so this is not time dependent. This is behavior that we would see over a short period of time. So shear thinning and thixotropy are two things that a lot of times people get confused, but those are different things. So next, why is concrete thixotropic? Well, the reason is that when concrete is at rest, it forms a three-dimensional network. There tends to be flocculation due to van der Waals attraction and Brownian motion. Particles stick together, they form a structure, and that structure causes an increase in the viscosity. When concrete is flowing, on the other hand, we begin to break apart those flocks. And so we have shear that's breaking apart the flocks. We also have particles contacting each other and having some flocculation. So the net result there is a decrease in the viscosity. So now, how do we measure thixotropy? So there's a number of different methods. I'm going to talk about three of the most common methods, and all of these methods, I'll point out, make use of a rheometer. So today, our session is talking about field measurements of thixotropy, and there are several rheometers that can be used in the field. As part of a project, you can use the rheology to correlate to the formwork pressure. And this is the one here that's used in the data that I'll show later. This is the icarrheometer. So it's basically a vane inside a larger container, and as that vane spins, we apply shear across the material. So the three methods I'm going to talk about are the hysteresis loop test, which I showed a little bit before, the constant shear rate test, and the stress growth test. So, like I said, you've seen this before. This is a typical rheometer. We increase the shear rate, and then we decrease the shear rate. And we measure the area between this curve. So initially, the concrete is at rest. We increase from 0 to maximum. We hold that maximum shear rate constant for enough period of time to fully break down the thixotropy. And then we decrease the shear rate back down to 0. And we calculate the area between the up and down curve. And the bigger that area, the greater the thixotropy. The next test is a constant shear rate test. And so what we do here is we measure the shear stress over time. So again, our concrete is initially at rest in a rheometer. We apply a constant shear rate to that test. And we look at the change in shear stress over time. So as we go from an initial shear stress from rest to this equilibrium shear stress over time, the difference between those two is the amount of thixotropy. And the greater that difference, the greater the thixotropy. Our third method is the stress growth test. And so with this one, again, we put our concrete in a rheometer. It's initially at rest. And we begin to turn the rheometer at a very slow speed. And what's happening is we are shearing just this material that's in orange here, right around the inner cylinder where we're actually turning that cylinder or that vane. And so we get an increase in torque or an increase in shear stress over time, and eventually we reach a maximum. So that's where we're initiating flow, and that's the static yield stress. So we're getting a little bit of strain over time, and then we start to get flow where we reach this maximum. And so we just pick off the maximum from that graph, and that is the static yield stress. And so again, the higher the static yield stress relative to the dynamic yield stress, the more thixotropy that we have. So one note of caution when you are measuring thixotropy is that it is very important that the concrete be handled consistently from test to test. So taking the concrete, putting it in the rheometer or whatever other device is being used to measure thixotropy, having it there for a consistent period of time, and then when you actually run the test, running a consistent protocol every time so that the results are comparable. So for example, in our hysteresis loop test, if we used a different set of speeds from test to test, we would get different results. So that needs to be very consistent. Likewise, if you put the sample in and you let it sit for a minute versus 5 minutes, you're going to get different results because of the time dependency of thixotropy. So how does thixotropy relate to formwork pressure? So first of all, we've known for many decades that the reality of the concrete is related to formwork pressure. So if you think about slump, the higher the slump, higher the formwork pressure. And as we go to SCC, we just get more and more pressure. So we know that. But when you look at SCC, not all SCC is the same when it comes to formwork pressure. There's another term in there that's really important to us, and that's where the static yield stress comes in. So when you put the concrete in the forms, initially it's very fluid. It has a high formwork pressure, but over time that thixotropic structure builds up, and the formwork pressure is reduced. So the more the thixotropy, or the higher the static yield stress, the higher or the lower we're going to have in our formwork pressure. And really, it's the static yield stress. So the thixotropy is helping us to increase the static yield stress, but it's really where we end up on the static yield stress. So if we start with a high dynamic yield stress and have a small thixotropy, that might be just as well as having a very low dynamic yield stress and having a bigger thixotropy. So when we're designing an SCC mix, we're making this trade-off. We want a low dynamic yield stress so it flows under its own mass, self-consolidates. On the other hand, we need a high static yield stress, and we can provide that through thixotropy. So if we think about a typical concrete delivery from the time it's batched to the time it's in the forms and beyond, you can see what we have here is this is time for mixing and our yield stress. So if you think about our dynamic yield stress, we want the dynamic yield stress to be low, and we want it to stay low. But we want that static yield stress to actually increase. So when the concrete is in the forms, the black line is what's actually happening. So we batch the concrete. While it's in transit, we're partially agitating it, so our yield stress is actually somewhere in between the maximum for static yield stress and the dynamic yield stress. Then we apply high shear, because right before we place the concrete, we're probably going to mix it. We're going to put it in a pump line. We're going to break down all that thixotropy. And then we get it in the forms, and that static yield stress starts to go back up. And so if we were to go back and vibrate that concrete when it's in the form, or apply some kind of agitation, we would have a decrease in the static yield stress, and it would go back down to the dynamic yield stress. So again, we need thixotropy. Thixotropy is important. It helps us reduce the formwork pressure, but we don't necessarily want too much thixotropy. So there are disadvantages to having a lot of thixotropy. We can have cold joints, for example, if we have two different placements of concrete that are coming together, and the first is very thixotropic, they don't blend well. And if we're not applying vibration, we don't have the opportunity to get those blended. Second is poor pumpability. So if you have this material that you're trying to, it's at rest, you're trying to start pumping it, and you have initially very viscous material before you can break that down. Pumpability can be a problem, and then also restarting placement after rest. So let's say you have the concrete in a bucket, and you're placing it with that method, and then you have it in the bucket for a period of time, and then you open up the bucket. If it's that thixotropy has built up, it's not going to have the same level of flowability as it did initially when you put it in the bucket. So let's look at field data. I'll leave a lot of field data for the other speakers, but this is some work that was done actually with Ellis Bond Construction, and I have the reference here, but you can see basically on the right are the measurements of the form pressure, and you can see that, for example, here these are the different cells, and you can see that as we initially place concrete in the forms, the lateral pressure builds up, and then it reaches a certain maximum, but then as we add more and more concrete, it continues to go up, but not at the same rate, because we're getting some of that thixotropic structure at the low concrete in the form, rather than that is not giving us as much pressure. So if you look on the left here, we have three mixes. So mixes 1 and 2, you can see had a very fast increase in yield stress and thixotropy. So you can see this is the mix 1 and 2 here, and that thixotropy increased very quickly. Mix 3, on the other hand, had a much lower increase in the thixotropy over time, and so mix 3 had much higher formwork pressure than mix 1 and 2. So this confirms that Thixotropy does in fact reduce formwork pressure. So to wrap things up, first of all, we have to have Thixotropy to have to make SCC practically. And we have our definition. It's the reversible isothermal time-dependent decrease in viscosity. And just as important as the decrease in viscosity is the increase in viscosity when concrete is at rest. And to get to successful SCC, we have to balance the need for a low dynamic yield stress with a high static yield stress due to Thixotropy. And if you can balance those right, we'll get good self-flow and we'll have a reduction in formwork pressure. So, thank you.
Very good introduction to Thixotropy, or Thixotropy, some people refer to it, which is a new buzzword in the concrete science and technology. But this is going to be something we're going to be seeing quite a bit today as intrinsic characteristics of the concrete that is affecting form pressure. So any questions for Eric, please?
Question, if you have a 100-foot wall, 10 foot high, 12 inches thick, and let's say we used to pump 2 foot at a time and go all the way across, when we do self-consolidating, do we continue using this, or can we fill it all up within an hour?
So you do want to control the rate. I mean, the rate of the pouring is
We still go by the old days of the old rate of pouring that we used to do with a crane and bucket and.
Yes. I mean, basically the higher the Thixotropy, the faster you can make that rate of pouring. But the rate of pouring is still very important. Is to control that. If you have a highly thixotropic mix, it will build up the structure and reduce the formwork pressure and enable you to pour that concrete faster.
Okay, thank you.
Yes.
In your stress growth test, can we use the ratio of the peak stress to the stress after it levels off also as an indicator?
Normally that's not done. So when you're doing the static yield stress, if you go back to that. So normally when you're running this test, the geometry is well defined when you just start that flow, and you're calculating the static yield stress based on the surface area of this cylinder. So you know exactly the material is being sheared, and you can do the calculation directly. As that material comes down and reaches this equilibrium value, you don't know the area or the volume of concrete out here that's being sheared, so you can't really do a direct calculation of that. And so from being a very direct, exact measurement, it's not something that you can really compare.
Okay. Any other questions? Okay. I'd like to thank the speaker for the very good presentation. Thank you very much. Speaker.